It's my great pleasure to introduce today's speaker, Professor Ann Sickles. Professor Sickles received her PhD in physics from Stony Brook University. After doing research at Stony Brook National Lab, she joined the department here in 2014. Professor Sickles' research focused on an exotic state of matter that existed only at the beginning of the universe. But amazingly, these days, scientists can actually recreate and study that matter in labs, in colliders. So this is what Professor Sickles will tell us. Let's welcome Professor Sickles.
Okay, well, thanks for coming. Thanks for spending part of your Saturday doing physics or listening to physics. So what I'm going to tell you about is called the Quark-Gluon Plasma. It's the hottest matter in the universe, and as Liang was saying, now we're able to actually recreate that in the lab. And so that's what I'm going to tell you about today. So I say something is the hottest matter in the universe. That's an absolute scale, but how hot is it compared to things that you might know about? Well, today is going to be a nice day. We don't have any beaches, but a nice day is 80 degrees Fahrenheit, right? This is pretty hot. Lava, which I think we can all agree is too hot to touch, is about 2,000 degrees Fahrenheit, so that's something you really should be careful with. An 80-degree day, you're okay. Lava, you should take some more precautions. It can really mess up your day. The center of the sun, which we can all agree is really hot. It's 28 million degrees Fahrenheit. Okay, that's pretty respectable. It's the hottest place in the solar system. A supernova. So this is the collision of, this is an exploding star. So this is quite a bit hotter than the sun, but a supernova rings in at about 150 billion degrees Fahrenheit. What I'm going to tell you about today is the Quark-Gluon plasma, and it's 5 trillion degrees Fahrenheit. And I can't download a picture off YouTube. So that what I'm going to do is I'm going to try to explain to you how we do this in the lab. What we're doing to try to build a picture of the Quark-Gluon plasma. So the way we do this is I have to take a little bit of time and explain to you what matter is made out of, the stuff that you see around you. So you see atoms. You see atoms that are formed into molecules and solids, you know, the wood. That was the biomolecules that were in this tree at some point, the tables, the chalkboard, all of this is made out of atoms. And atoms are interesting because they're mostly empty. This is just a picture I took off Wikipedia, and it shows an electron's orbit. So the electrons, there's a few electrons in every atom. It depends on which atom you're talking about, how many electrons there are. But they're very small, point-like particles that circle around what is the nucleus of the atom. And the thing about the nucleus is that's where over 99% of the mass of an atom is this nucleus. And an atom is about 10 to the minus 10 meters. We call that an angstrom. And the nucleus is a few Fermis across. And what the heck's a Fermi? A Fermi is 10 to the minus 15 meters. And so that's how big the nucleus is. And so everything that you see around you, the mass is coming from the nucleus, and the nucleus is incredibly small. The vast majority of the atom is really empty space. So what we're going to do is we're going to take a close look inside the nucleus, and then we're going to use the nucleus to create the Quark-Gluon plasma. So nucleus, 99% of the mass of normal matter is in the nucleus. And the nucleus can vary in size from hydrogen, which is the lightest, to uranium, to all the transuranic elements that are created in the lab. So these are small to large. It's composed of protons and neutrons. So those are the building blocks of the nucleus. So the proton carries a +1 electric charge, and the neutrons, they don't carry any electric charge. And that's what I've illustrated here. I'm not sure, this is just a PowerPoint drawing. If a proton should be red or blue, it doesn't particularly matter. There's 2 kinds of constituents in the nucleus. In the nucleus, what holds these things together? What holds together a bunch of protons in the nucleus? Well, it's something called the strong force. And the strong force is strong. It's incredibly strong. And so what it does is it keeps all these protons together. They all have the same electric charge. You might think that they should blow up, but they don't, which is why we're here. And they're held together by this strong force. And there are 4 fundamental forces in nature: gravity, electromagnetism, which are the 2 you're most familiar with, but then there's these 2 nuclear forces, the strong force and the weak force. Physicists maybe are not always the most creative namers, and I'm going to tell you about the strong force. So it's very strong, and it's also very short range. So it doesn't impact your daily life so much, except for the fact that it holds the nucleus together and makes everything else possible. Okay? So what's inside protons and neutrons? They are not point particles. They have substructure. And they're made out of these even more exotic particles, quarks and gluons. And these are the fundamental particles which interact via the strong force, or quarks and gluons. And they were derived they were discovered in the 70s. So that's why they have whimsical names. The quarks, they carry electric charge. This is where the electric charge of the proton comes from, is from the quarks that make it up. And the gluons, they exist to bind quarks together, more or less, and hence they're called gluons. And so you might have learned in high school chemistry, as I did, that the proton is made up of 3 quarks. And so that's what I've drawn here. This is my proton as a PowerPoint circle and 3 quarks as letters. But actually, the proton is a quantum system, and it has an extremely rich structure. So there's a whole bunch, and this is just when I got bored of drawing these circles, or these letters here. It has a whole bunch of quarks and gluons inside of these. These are virtual particles that flicker in and out of existence. But that's really what is made up of the protons. And the neutron looks pretty much the same way, at least from this level. What is interesting about the strong force is that this quark all by itself, the strong force does not like that. It has a property called confinement, which doesn't let you have that. So all quarks and gluons in nature, in the natural state of matter, have to carry no net charge according to the strong force. The charge in the strong force is called color, and everything has to exist in these colorless objects. You can't have a quark by itself, and that's really a fundamental property of the strong force. And because you have this confinement property, this is why you don't have an intuitive feel for how the strong force works. Because you have a feel for how electronics works, because you can plug things into outlets. It's very accessible to you. Electrons are all over the place. You see lightning in the sky. That's electric discharges. But confinement makes that all those things about the strong force are really wrapped up inside these protons and neutrons, which are 10 to the minus 15 meters across. So it's really remote from your everyday existence, despite the fact that it makes up a huge fraction of your everyday existence. So this is what makes the strong force hard to study, is the property called confinement. So, normal people might give up at this point, but physicists, we like to dig in. So what happens? What if I want to have free quarks and gluons? What if I want to have a system that's made up of quarks and gluons rather than protons and neutrons, which are then themselves made up of quarks and gluons? So what we want is a system that is hot and dense enough to essentially melt the protons and neutrons. That's what we want to do. Just like I could melt my coffee cup if I held it over something that was hot enough, lava maybe. If I held it over that, I could melt that. Well, if I could find enough energy, maybe I could melt these protons and neutrons and have a system that's really made up of the fundamental quarks and gluons. Okay, so what I need is I first need to start with something that's made up of a whole lot of quarks and gluons. And for that, what we use is the lead nucleus. And it's not particularly important that it's lead. It could be anything. We want something that's big. Lead is a heavy nucleus. It's made up of many protons and neutrons, which are then themselves made up of many quarks and gluons. And so this is a good place to start. Then, just like with my coffee cup, I want to add energy. I want to have something to heat it up. I can't use a Bunsen burner or lava or anything like that because it's not hot enough. It doesn't provide enough energy. So what we do is we actually add another nucleus, and we smash them into each other. And then that takes the kinetic energy from these 2 nuclei coming at each other, which are going over 99.9 whatever, the speed of light, and the kinetic energy that these 2 nuclei bring when they smash into each other liberates these quarks and gluons. And that is essentially what we're doing, and that is how we create the Quark-Gluon plasma. And this is interesting for two reasons. The first of all is because there's only 4 fundamental forces of nature, and so studying how one of them changes when you heat it up is intrinsically interesting. The other one is that this is actually what the universe looked like about 1/millionth of a second after the Big Bang. So this is actually a window back in time. So we're not only doing something which is intrinsically interesting, but we're learning more about where we came from as inhabitants of the universe. So I can't do this here for you today. There's no demonstration on this. It would be tremendously unsafe. We'd all have to take radiation training. There's 2 places in the world where you could do this. There are particle accelerators. This is what you use to do it. The first one that I'm going to talk a lot about is the Large Hadron Collider, which is in Geneva, CERN. It's big. It's very huge. It's something like 16 miles around. It's underground. The collider actually goes over the French-Swiss border in a couple of places. It has very high energy collisions. I'll come back to that at the end. And so that's where the Large Hadron Collider is. We also have a collider in the US, which is called the Relativistic Heavy Ion Collider. It's on Long Island in New York at Brookhaven National Lab. It's a lower energy collider, but there are reasons that it's actually particularly interesting, which I'll talk about at the end. And so these are the only 2 places in the world where one can do this. And so I'm involved in experiments at both, and I'm going to tell you a little bit about this. But first, I'd like to show you a YouTube video, because who doesn't like YouTube videos? This is one that was put out by CERN, and it shows you a little bit about how these colliders work. And what I want you to take away is that these things are incredibly complicated. So there's CERN in the middle of Europe. There's Lake Geneva. There's the LHC. And what you see is there's this whole complex. I work at the Atlas detector, but what you do is you start out in these small things which are off the LHC. First, you have to have something which provides you with the nuclei, and so that's what happens here. You accelerate it using electric fields, and then you put them in these circular colliders where you use electric and magnetic fields to essentially speed up these protons. So that was the proton booster. And then after that, you get it going around in the proton synchrotron, which is a bigger, higher energy machine. These things were used for research once, and now we just use them as warm-ups. So when they're going fast enough, you put it into the superproton synchrotron, of course, which is bigger. There are Nobel Prizes associated with these machines. These are amazing machines. And then finally, you put the protons or the lead nuclei, whatever you're colliding, into the LHC. And so this is huge. This is the CMS experiment. They're my competitors, and many of my friends, actually. I work at the Atlas experiment, which is what's right here. And so what happens is at a few places around the ring, we bring these beams into collision. And then we measure the signals that come out in our detectors here. And the rest of this video, it goes on. It's about the computing challenges. And I think you can trust me that the computing challenges of dealing with this data are non-trivial, but that's not why you came. All right, so this is about how colliders work. There's more videos on this, and you can certainly watch the whole thing. So this is what I want to do. I want to take heavy nuclei. I want to smash them into each other and recreate this hot matter that's from the earliest moments of the universe. So just to set the scale, it lasts for about 10 to the minus 23 seconds, which is an unfathomably short amount of time. It's a billionth of a trillionth of a second, if you want to count the exponents. So I can't do anything to it. Once it happens, it exists, it goes on its own trajectory, but I and my detectors and anything cannot respond to it fast enough. It's 1 billion times smaller than the pixel on your iPhone display. So it's the size of this Quark-Gluon plasma is about the size of the nucleus. And so the lead nucleus is about 10 to the minus 14 meters across. And so that's about how big this Quark-Gluon plasma is. So that's why there's no picture. And this makes challenges for an experimentalist. I'm an experimentalist, and physicists use challenging when something sounds impossible. And it's just a way to make sure that we can suitably impress people when we finally do it. So I work at the Atlas detector, and it's huge. That's really the only way to say it. I've ever actually seen it. It's deep underground, but many people do go down there. It's 25 meters tall, so a meter is about 3 feet, so it's about 75 meters tall. These are people, little artist rendering of people. That's about the size you would be if you were standing on the Atlas detector. 44 meters across. So that's about 150 feet across. The collisions happen here in the very center. And the detector's built like an onion. You just keep going out, more and more detectors, different ways of measuring what comes out. So just some statistics. There's 100 million electronics channels, 3,000 kilometers of cables, 7,000 tons, millions of lines of code. 3,000 people are needed to get physics out of this thing. From 38 countries, it's truly international. Collisions every 100 nanoseconds. Most of the time they collide protons looking for new particles, but that's not really what I'm going to tell you about right now. Those people are my friends, but I'm going to tell you about the Quark-Gluon plasma. So our output so far is 800 science papers and 50 million emails and hundreds of thousands of doodle polls trying to schedule meetings. Okay, so what do we actually see? We see hundreds or thousands of new particles created in each collision. So we take this, we make this Quark-Gluon plasma, we turn energy, and then it, of course, expands, and it cools off because it doesn't last very long. It's over really quick. And so this energy that was in the Quark-Gluon plasma has to go somewhere, and so we make particles. This is an artist rendering of some of these particles. And this is exactly according to the most famous physics equation, E equals mc squared. We take this energy and we turn it into massive new particles. And since we can't do anything to the Quark-Gluon plasma, these particles really provide the only window we have into the collision. So you can think of it like reconstructing a car accident from the patterns in the glass. Right? This is what we have. We have the remnants. And we have to sort through them and try to figure out what happened in some particular collision. And we look at each collision independently. So a collision is the result of two lead nuclei smashing into each other. We look at that independently. But then we look at billions of these collisions. So they're all different, and we try to look for the patterns in what we see. That's really what we do as experimentalists. So this is the slide that I had up at the beginning. So this is a very head-on lead-lead collision. And this is the green and the blue here is a model of what the Atlas detector looks like. And the orange lines, each one of those is a particle that was created in a single collision and tracked through our detector. So really we can have up to 10,000 particles created in the most head-on collisions. So now I've started to talk about head-on collisions, so maybe we should get into geometry. So what do actually nuclear collisions look like? And the nucleus is small. I already told you that. I said we use big ones. But what do nuclear collisions actually look like? And they look kind of like this. The nucleus, so this is gold, but it doesn't really matter. Gold and lead are they're both big. And so these two nuclei come in. One's coming in from the left, one's coming in from the right. One is red and one is blue. You can see they're offset from each other. You can also see that these gold nuclei have 197 protons and neutrons in them. And so these protons and neutrons, they're basically clumped into like a ball shape, but there's fluctuations. The protons and neutrons can move around. This is a simulation of how one looks. So you see there's some that are, barely hanging on, and then there's weird structures. Each one's a little bit different. And these nuclei, nobody makes them come in exactly head on, right? We don't have the ability. You have a question?
Yeah.
Yes.
Are these nuclei stripped of their electrons?
Yes, they are fully stripped. So these are plus 79. So they have a huge electric charge, which is a totally interesting field, but not anything I'm going to talk about here. But they have a huge electric charge at this point. So they come in, and they can hit at whatever impact parameter they want to. They can miss each other, and a lot of times they do. They can hit where they're totally head-on, and then they can hit where they're offset with each other, as you can see here. So this one, the nuclei are offset, the centers are offset from each other by 6 Fermis, which is not a lot to you or me, but it's a lot compared to this nucleus size. So here they come in, and what I've done is that the darker protons and neutrons are those that interact, and the lighter ones are the ones that miss. And because these things are going pretty much the speed of light, they don't have time to figure out that they missed. They come in, they hit, and the things that miss just keep going down, keep going because they don't know that their friends got into this massive collision. They missed out on that. So we can rotate this view a little bit. And so now I've just rotated it 90 degrees. So one of the nuclei is coming in, one of the nuclei is going out to the screen. And so what you see is this region where they overlap with each other is kind of like a football shape. And if you just, you draw two circles, you see exactly that that's probably what should happen. And the football shapedness, essentially, of the region where the collision happens depends on how far offset these things were with respect to each other. So they all look different. So these are 3 different ones with different impact parameters. So here the impact parameter, the nuclei are offset a lot with respect to each other. Here they're offset less. And here they're offset almost none at all. So you can see the nuclei have a little different shapes. In general, though, this is more circular, and this is more football-shaped. So what are we going to do? Do you have a question?
Are these collisions elastic?
No, these are inelastic. We really blow things up and create new particles. So this is just one of these collisions. And the first thing you can do is you can count the directions that all these particles come out. All these orange tracks that I showed you a few slides ago, you can just count where the particles are. And this is what we do. In physics, I teach the freshmen, we always have to define a coordinate system. You have to know what you're doing. All right, so here's my coordinate system. It wouldn't be a physics lecture unless I threw in a Greek letter, so we're going to call the angle phi. And we're just going to count the number of particles. This is a relative number of particles, so we just put it at 1. So this is the number of particles that come out with respect to this angle phi. It's in radians, because for physicists, that's what we like to do. So this is the stuff that comes out this way is at 0 here. Pi is over here, so that's there. And pi over 2, which is here, is the stuff that comes out the top and the bottom. So what you see is that the number of particles varies a lot depending on how you come out of this collision. Varies, plus or minus 20%. That's kind of interesting. So we see less particles that come out this way, the top and the bottom, from the ends of the football. And we see a lot more particles that come out the long side. And if you are lucky enough to be making a measurement and see a huge effect like this, this is great. You take it and you write it for all it's worth, right? And so that's what we do. Because this gives us a lot of physical insight. What's going on? If you just imagine that in your football, you just had a few particles, then the density is very low. And any particle, no matter, say this particle here, no matter which way it tries to come out, it's very unlikely that it's going to hit anything else. There's just not a lot of particles. Most of it is free. It's just like if you try to walk across the street and there's no cars, it's at 3 a.m., nobody's around. You're not going to run into anybody, no matter which way you walk. But if you try to walk around the quad at lunchtime or Green Street at lunchtime, you're going to run into a lot of people, right? But if the density is low, you're not going to run into anybody. If you increase the density, now this particle here, it's easy for it to come out this way. Any way it tries to go that's inside, it's going to hit a lot of particles. And so what this variation in the angles that the particles come out is telling us is that the interactions must be important, that this must be important in the collision. Because in order for you to have any sort of variation in the angles that the particles come out, they have to know that the other particles are there. And the only way they can know that they're there is if they're interacting with them in some way. So we know the density is high. And actually, working with our theoretical colleagues, what we have is we have actually the limit of a lot of interactions. So what I've drawn here is it's a rainbow-colored set of circles, right? So this is high density. These are lower densities. And obviously to me maybe, outside the collision region is just vacuum. These beam pipes, there's nothing else in the LHC except for the particles which are colliding. So we know the density is 0 outside of our football. It's very high in the middle. And so what we have is we have a steep pressure change here and a very strong or gradual pressure change here. And so one thing you can think of this as is think of this like a topological map, right? This is the top of the mountain. This is the equivalent of jumping off a cliff, right? It's a very steep decline down. This way is more like going down the garden path. This is a very slow side down. And so what happens to the Quark-Gluon plasma is it explodes outward because there's a huge pressure change. Just like falling off a cliff, it explodes outwards in this direction, and it does not explode outward in this direction as much. And that's why you see more particles coming out this way than you see this way, because it's really exploding outward. And this is characteristic of how a liquid works. It's the limit of huge amounts of interactions. This is how a liquid works. This is what happens in water, liquids in your daily experience. So how do you characterize a liquid? There's lots of different ways you can characterize a liquid. I'm going to talk about viscosity. So you have an intuitive feel for viscosity, right? Water, right? You can support waves in water. You can have ripples in water. All of these things. Water is a very low viscosity liquid. It's generally a very good liquid. You can describe it well. The theory of how you describe liquids is hydrodynamics, because water is a very good liquid. Honey is a much worse liquid. It has a higher viscosity. You know this. The ripples that you see in the waves in this nice picture from a family vacation to Hawaii, they have a lot of structure. This jar of honey has no structure. You know that you could not get that kind of structure with something with the viscosity of honey. So by looking at these variations, we know that the Quark-Gluon plasma is actually supporting a lot of ripples. And what we can do is we can use models to actually take these ripples and try to figure out what the viscosity of the Quark-Gluon plasma is. And that is something that we've spent a long time doing in this field. So viscosity, we typically write it in terms of this funny quantity, eta over S. Eta is the viscosity. S is related to the disorder in the system. So if we write it in these units, now I've got a lot of Greek letters, right? I have eta, and I have pi here. So it's 25 in units of 1 over 4 pi. And these are funny units, and I'll get to it in a second. This is the viscosity of water. So we already know water is a very good liquid. If we measure the viscosity of the Quark-Gluon plasma, it has a viscosity in these same units of less than 5. So water is actually about a 5 times better liquid. No, other way. The Quark-Gluon plasma is about a 5 times better liquid even than water. And we already said that water was really the prototypical liquid. So interestingly, why is this important? Why do I use these units? Because there's a calculation in string theory. 11-dimensional black holes and a theory that was kind of like the real theory of the strong force, but not quite. And there's a conjecture that there's a universal quantum minimum to how good of a liquid you could have. And that is at this 1 over 4 pi. So it's possible that if we are able to quantify the viscosity of the Quark-Gluon plasma, we would actually be testing a calculation that has to do with string theory. And string theory, I don't know how much you know about it, but one thing about it is it's not readily experimentally testable. So there's a lot of interest in being able to see how these two things fit together. Bringing down this bound here and trying to understand if this bound is violated or not. So this is a very important question to us, determining what the viscosity is. However, there's another question, and that's why. Why should the viscosity of the quarks and gluons at 5 trillion degrees, why should that be so big? What about the strong force leads to this fluid behavior? And this is actually the question that I want to answer. Because it's inherent in these understanding where this comes from. And to answer that question, we need a picture of really what's happening inside the Quark-Gluon plasma. We need to zoom in. You think about, all right, you know that water is H2O. That's the chemical formula for a water molecule. That doesn't tell you why water at room temperature is a liquid and why water at 32 degrees freezes. So we have a descriptive understanding of the Quark-Gluon plasma, but we then want to get at an understanding of why. And so that's what I want to talk about here. We need a microscope. So this is now my cartoon Quark-Gluon plasma. It's right there. This is exactly what it looks like if I draw it on my computer. And I want to do something like an X-ray of the Quark-Gluon plasma. Right? You break your arm. The doctor wants to take a picture, so he takes X-rays and he shoots them at your arm and looks at what comes out. this is exactly what I want to do here. I want to shoot something through the Quark-Gluon plasma and look at what comes out. I don't want to use X-rays, though. I want to use something that interacts via the strong force. So what I'd really like to have is a beam of quarks or gluons and shoot them through my Quark-Gluon plasma and look at what comes out. Now, I don't have such a thing. So again, this is an experimental challenge. And so I'm going to talk to you about how we're trying to do that. Well, actually, I told you that a proton is made up of quarks and gluons, right? So if I have two protons that are coming at each other, this is kind of like two beams of quarks and gluons shining right at each other, isn't it? And sometimes, if you get lucky and wait long enough, a quark from one proton really hits a quark from another proton head on. And when that happens, they exchange a lot of momentum, and you get a quark coming out this way and a quark coming out this way. So now I have taken my beam of quarks and gluons from these two incoming protons, and I have scattered two of them, one coming out this way and one coming out the other way. Because, of course, we have to conserve momentum, so they have to come in pairs and they have to be back to back. And, of course, confinement kicks in. Nature does not like my free quarks scattering out at high energy. And so I'll talk a little bit about this, but, of course, in the end, what we observe is a bunch of particles. And those are represented by those arrows here. These are just a bunch of particles, things like protons and neutrons that come out at the end. So we observe this. This is an event display from Atlas. So this is a real event, a proton-proton collision, and there's a lot of details on these plots. This is the view where one proton is going into the screen and one proton is coming out. And these yellow spots here and the green are proportional to the amount of energy that was deposited in the Atlas detector. And so you see that there's a lot of energy this way, and there's a lot of energy that way. So those are your back-to-back, we call them jets. So this is a pair of jets. They're back-to-back to conserve momentum. If you imagine cutting the detector and unrolling it like you would with a paper towel tube, and then looking at the energy, which is what's shown here, you can see these are these two energy deposits. They're really the only thing that happened in the event. So this is what you see. These are the jets. So if I take my beam of protons, and then I just cover them up with a whole bunch of other protons and neutrons, well, this is just like using my lead collisions, right? So there are certainly protons in this lead nucleus, protons in this one. The same idea works with neutrons as well. So if I just take two giant nuclei and I run them into each other, I will create a quark-gluon plasma, and sometimes these quark-gluon plasmas will have going through it these two jets, just like I was showing you before. So that's what we're going to use as our microscope. We're going to use these fast quarks and gluons that are created when a quark from one proton or neutron hits head-on a quark from another one. And so that's how we're going to use it. That's what we're going to use for our microscope. So it can happen anywhere within the quark-gluon plasma. I've had it happen here at this place where the star is. So you have one coming out this way, one coming out this way. It could have happened anywhere. This is just where I drew it. And then, of course, it turns into a bunch of particles. That's what I've shown here, again, by these arrows. These are the particles from one jet, and these are the particles from the other jet. So the question is I can show you PowerPoint drawings all day, but what about the data? This has got to be better. And so we did this. And holy mackerel, I don't see a pair of jets here. This is the equivalent plot of the unrolled detector that I was just showing you. I see one jet. And I don't know, if I squint, I may be able to convince myself there's a little something extra here where the other jet should be, but I certainly don't see the same visual clarity that I did before. And that's troubling, right? Because physicists, I believe a few things, and one of them is very deeply, I believe in momentum conservation. So if you tell me something doesn't violate momentum, or violates momentum conservation, I get very upset. And I generally don't want to be upset. So, all right, let's take a look at the energy of these jets. I mean, this is just one event. Anybody can wiggle their way out of one event. This is not statistics. This is just an anecdote, right? So we did this measurement, which I've shown here. So this is a plot of the energy of one jet over the energy of the other jet. I called one jet 2 and one jet 1. It doesn't particularly matter. They're both the same. And what's shown in the blue points is proton-proton collisions. So this is where we have these beautifully balanced jets that I showed you first. What's shown in the red points is collisions between two lead nuclei. And so if the jets are perfectly balanced, you should be at 1. The ratio of these should be 1. If the jets are imbalanced, you should be away from that. You can see the blue points are not actually perfectly at 1, though 1 is the most probable value. And that's because the strong force is really complicated. And there's great stories in why this is a distribution, not just a spike at 1. But the lead collisions are troubling, because really it does seem like the most probable value here is that the second jet has half the energy of the first jet. And so this event display that I showed you here is not a fluke. This is really what's going on. And so there it is in plot form with error bars that are shown here. There's really no getting around this. We're seeing something that's totally different in lead-lead collisions than we are in proton-proton collisions. As an experimentalist, this is fantastic. When I first saw this plot, I almost fell off my chair. I mean, it was amazing. I remember the day I could tell you about it. This is amazing. So we've got a lot of energy that's removed from Jet 2. This is great. This tells us that our microscope is interacting. If the jets just went totally through the Quark-Gluon plasma and they changed nothing, then what's the point? It's not going to work. But since they do change, this tells us that we have the opportunity to learn something. So now I've revised my picture. So we've got this one jet here. And this jet doesn't see very much of the Quark-Gluon plasma. Its path is rather short. But then I have this poor jet. And that has a long path through this very hot matter. And so the energy of the particles is reduced. And what I've shown here in these blue arrows is a lot of stuff that comes, the other particles that come from the interactions of the jet with the Quark-Gluon plasma as it's going through. These are the lower energy particles, so the arrows are shorter. So how do we understand that? And to do that, I have to tell you a little bit about how a jet is made. I just had arrows that went to more arrows, and I kind of waved my hands. But this is how a jet is made. I said that nature doesn't want you to have a free quark, and I said that jets come from a quark which had hit another quark and then scattered like a billiard ball. So how do we reconcile these statements? Well, you start out here. This is my quark, represented by this arrow that's going along here. And it tries to progress forward in time, going this way. So this is it going along. And nature starts to impose confinement. The strong force says, no, you cannot just be a bare quark. And so this is a gluon. Of course, nature doesn't like a bare gluon either, and so it starts to make more and more particles. And we call this dressing, essentially. So that's what's happening. Nature is dressing up the quark with more and more quarks and gluons. And eventually, these things become lower and lower energy, and they become the particles that we observe in our detector. So it's like a shower process. You start with one thing that makes two things, makes four things, and eventually what you have at long times is you have the particles that we expect to see, and this is what we measure in our detector. And it's really the process of dressing up these quarks and gluons. The Quark-Gluon plasma changes that. So what I've shown here are more gluons. These are the gluons from the Quark-Gluon plasma. And again, it's just a cartoon, but there's more interactions. And so this dressing process happens differently in the Quark-Gluon plasma than it does when there's no Quark-Gluon plasma. And this is really the key. This is what allows us to have information. So if we can take the jets that we observe and sort of go back to how they must have interacted, what these interactions that are shown here in red must have looked like, that's how we find things out. That's how we use the jet as a microscope. So essentially, we get more particles, they have different energy, and it's because of these red interactions here. And so that's what explains the blue particles here. It's not just a cartoon. I measured it. So this is a plot that was made by my group. It was done here. I made this plot myself, actually. Much blood, sweat, and tears. So this is the number of particles in a jet. We like to take ratios. A lot of things help experimentally when you take ratios. So this is the number of particles in a jet in lead-lead collisions divided by the number of particles in a jet in proton-proton collisions. As a function here on the x-axis is the particle energy. And you can see at higher energies, there's not so much difference. At lower energies, there's this huge excess. It's a 50% excess for all of these jets. And that really is these blue particles, these extra low-energy particles that we see in lead-lead collisions compared to those in proton-proton collisions. So I've told you about what we've seen. This is a paper that came out at the beginning of the summer. What are we doing next? Well, there's two things that are really, I put a lot of my time into. One thing is that we work with theorists to build models, which tell us how to turn this cartoon into these measurements. So they do calculations and predict measurements, and we make measurements and try to compare them to their theory, and we work together to try to determine what are the most useful measurements to make. So I have 3,000 collaborators on ATLAS. There's 2 other collaborations that do a lot of these sorts of measurements, CMS and ELISE, at the LHC. And then there are lots of groups of theorists that make these models. So this is a very interactive field, hence all the doodle polls, all the emails. We have to talk to each other. There's no simple roadmap. The other thing is, as an experimentalist, we're kind of crazy, obsessive people. I try to figure out how I can, everything I can about this process. So how this depends on the size of the quark-gluon plasma, the energy of the jet, the type of quark, the temperature of the quark-gluon plasma, whatever. And so I get graduate students and postdocs, and we go at it, right? This is what we do. This is what makes us happy. So I want to tell you a little bit about what we're doing to try to understand how this depends on the temperature of the quark-gluon plasma now. So I told you there were 2 colliders. I told you a lot about the LHC. I showed you a video. I didn't tell you about this relativistic heavy ion collider in New York. So you don't know what a TeV is, probably. But at the LHC, the collisions happen at 5 TeV. At RHIC, they happen at 0.2 TeV. So there's this factor of 25 difference. And the interesting thing is that the collision energy sets the temperature of the quark-gluon plasma. This is the key. It's how fast they're going that tells you how hot your quark-gluon plasma is. And it's not like your stove where you can just turn it down. The LHC does not run well at 0.2 TeV. It's like trying to drive a sports car in traffic. You're just going to get upset. So this runs very well there. So what we do is it's actually much more efficient to use 2 machines. And so that's what we do. We vary the energy of we use both machines to vary the temperature of the quark-gluon plasma. Because if you want to study it and you don't know how it depends on temperature, you're missing a huge slice of the pie here, right? If you didn't know how water depended on temperature, you'd miss ice and water vapor. You'd miss all sorts of things. So in order to do this, we have to build a new detector. So RHIC has been running since 2001. And people weren't asking these questions in the 90s when the detectors were designed. But now, especially driven by the LHC, we're asking these questions. And so we want to go back and look at RHIC again. But the detectors are not the right detectors for it. And so we're building this detector called S-Phoenix. And so it's currently under construction as a new detector at RHIC, which is optimized for these jet measurements. And so this is a long time work going. I was there in the room when it was first brought up. We've been working on it for, I think, 6 years now. We expect to take data in 2023. This is an engineering drawing of it. There's the person. You can see this is considerably smaller than ATLAS, as I showed you earlier. And the reason it's smaller is because we're at 25 times lower collision energy. So we don't have to detect as energetic of particles. So that makes things a little easier. We build our detector around a superconducting solenoidal magnet. And if that sounds complicated, it is. There's a decent chance that you buy one and you try to turn it on and it doesn't quite work. So we stole ours from the Stanford Linear Accelerator in the dead of night. No. It was the Department of Energy. There was a lot of paperwork, but they had one that had been used for an experiment which was decommissioned. And so we put it on a truck. There it is on the truck at the Stanford Linear Accelerator complex in the Bay Area. And we drove it across the country to New York, or the people who with this trucking company did. And so that's really what we're building our detector around. And you think building a detector is going to be in New York. Well, actually, we're making a big chunk of it here in my lab. I was going to say Urbanic, but actually the lab's in Champaign over by the stadium. And we're building these blocks. And these blocks, you can come up and see them afterward. These are, they're heavy. They're made out of tungsten powder. And they're this big. And they have, which maybe you can see, they're filled with plastic scintillating fibers. So we're going to build 6,000 of these blocks. And these are really an essential component of the jet measurement at S-Phoenix. So what happens is electrons or photons, they come in this way. This is really the last thing that they see. This is what the front of the detector will look like, or looks like. This is just a photo of this, which you probably can't see, a blow-up that I took with my phone. So they hit the tungsten, and just like what would happen to you when you hit a block of tungsten, they stop, and they start to create more particles. They have a showering process, which is very similar to what I told you about jets, only this is driven by the electromagnetic force. And this showering process creates a lot of light. And these scintillating fibers take the light, and they pass it to the front of the calorimeter. It's a calorimeter. They pass it to the front where we read it out on photosensors. And so our job at Illinois is to build these bricks. We're brick builders. I'm the blockhead. That's what I get to be. So this is really an essential component of this measurement. There's a nice picture of one. These are a couple of my undergrads working in a tent. It's a party tent, and the reason it's a party tent is because these fibers are hard to see. They're 0.5 millimeter across. So we have a high bay, but we needed something that brings the light down lower so they don't ruin their eyes too much. So there they are working on it. They're happy, trust me. So that's what we're doing here to try to learn more about the Quark-Gluon plasma. We work at the LHC. We also are building detectors for the future as well. So really what we're doing is we're using fast quarks and gluons as a microscope to study the inner workings of trillion-degree matter. We're doing this at 2 places, CERN and Brookhaven. And really, this is a new window into one of the 4 fundamental forces of nature, and a look back at the early universe. What I'm spending a lot of time on right now is getting ready for this new data that we're going to have at the LHC in November. Again, a lot of doodle polls and emails, but we're very excited about this. I'm really looking forward to it. We're also working hard towards a new detector to be able to understand the temperature dependence of this Quark-Gluon plasma. So, thanks a lot. So that's a really interesting question, and we don't know the answer to it. So we can't compress it in the way that you could try to compress water, but we do look at its I talked about the viscosity, which is a shearing viscosity, but there's also a bulk viscosity, which is a viscosity against expansion, and that's something that we're trying to study a lot right now, actually. Yes. So do you get to know how it started by this experiment? I think that the more that you can understand about it going this way, which is the way that is accessible from us now, then you can then feed that into models which take into account that the early universe started from very different initial conditions. So that's something that you have to take into account in your models.
Yeah, I was going to ask, you talk about the Quark-Gluon plasma as a liquid, right? Which intuitively makes sense. Intuitively makes sense it has some sort of viscosity. But what does viscosity really tell you about the fundamental interactions of a nucleus? What does it tell you about scattering and how these things happen?
So that's exactly what I'm trying to get. Why should that? And I don't know the answer to that. I don't have an intuitive picture. I'd love to be able to give a talk in 5 years where I did have an intuitive picture. But this is something we don't understand yet. This is where we sit. Yeah? Oh, sorry.
You said that in the Quark-Gluon plasma, which you create, there has to be a conservation of color charge. What's the corresponding symmetry to that?
So that's just a few. So they asked about the corresponding symmetry for color charge. So what nature requires, the fundamental theory of the strong force is called quantum chromodynamics. And so that enforces the color charge conservation. So we can talk about that in more detail later if you want.
I assume your Atlas detector is cool.
Yes.
So do things inside there melt? And also, does it get activated?
So parts of it do get activated. We have it cooled how cold you need it depends on the various technology of the detector components. We have a silicon detector, which is quite cold. Other parts of our calorimeter, we also have a liquid argon calorimeter, so you have to keep that at a constant temperature. The activated parts, actually, I was talking, remember, about the parts of the nuclei that get sheared off and they don't know their friends had the collision? Those go straight down the beam pipe. And so they end up at angles that are very close to the beam pipe, and that's where a lot of the activation happens. In the detector itself, it's generally safe to go down there unless the accelerator is on. That stuff is not so activated.
Got a question. So you're getting quarks and gluons coming out the inside, but in the Atlas experiment, by the time they get all the way out there to being detected, what particles are actually being detected?
So those are the normal particles of particle physics. So pions, kaons, protons, neutrons, B hadrons, D hadrons.
So you combine into neutrons
Yes.
by the time they get out there?
That is essentially what's happening in this dressing process, is going from quarks to going to the normal stuff that people who take particle physics classes hear about.
Will it tell us anything about photons?
No, this will not. The lead nucleus is remarkably stable, and we don't keep it around long enough to be able to make constraints on anything like that.